Okay? So this is before you hit resonance with one of the quantum dot. And these are just somehow the laser line. So this is the energy of the laser. And these are different quantum dots located at different spatial locations. So before you hit a resonance, sometimes you can still see this kind of scatter. These are non-resonant scatter light. Okay? But they scatter at the quantum dot energy, at the laser energy. By the time they hit near resonance with one of the quantum dots, then suddenly this quantum dot emits such a bright light. Okay? So this, we are scanning the laser energy. So on the spectrometer, you hardly see this energy scale move. But we do know that is the energy we are scanning. So you can see for this one, within only about 2 micro eV near the resonance, you see this thing sharped up. And then when you are about 7 micro eV away from that, you don't see resonant excitation. So then let's say, well, okay, let me just plot the intensity of this. So this is the detuning energy. That is the intensity we have. And if I plot the intensity here to here, the ratio is 1,000 to 1. Okay, of course, this is one of the best cases, 1,000 to 1. Most of the case we see is about 1 to 200 to 1. So the laser scatter background is less than 1%. So in the very favorable situation, it's even less than 0.1%. So the result was really far beyond we even imagined. And I would say it's far beyond anybody ever imagined. Okay. And so from that, we ended up knowing that how sharp this quantum dot is. Has 2.8 micro eV. And now we even have things right around 1 micro eV. Right? So 2.8 micro eV means about T2 time is right around this. And the T1, for this particular quantum dot, we didn't measure T1 directly, but then we look at a lot of other quantum dot. We can measure T1 time, and we can also measure T2 time. Unfortunately, for all the quantum dot we measure, we are not transform limited. That means T2 is not exactly 2T1. T2 is always smaller than 2T1. That means there are other decoherent mechanisms in there. They are pure dephasing in there. But still, this is really very, very sharp line. Then we can also see this, and we can take this quantum dot, and we can use a laser. But in this case, we use a pulse laser. Then we can map out all the excited state. And usually, if you show this movie, then as I scan the laser line energy, and then pass, when you hit the resonance, this thing just light up very bright. So that, then we can also, so in this one we have about 8 micro eV. Then if you also take this emitted light and then you look at the this energy, and then at this time we do the excited state excitation, then we look at the photon-photon correlation, then we see this anti-bunching. So all signature indicate this is a single dot, this is a quantum emitter. Now, again, I indicated earlier when we try to do this Rabi oscillation control, when we control the exciton vacuum and exciton excited state, really, its quality factor is not that high. Okay? Now, once we can control this ground state, we know this ground state lifetime, suddenly many hundreds of picoseconds is about another order of magnitude longer than what we did for the exciton excited state. So presumably its coherent time is a lot longer, and indeed we now do the Rabi oscillation. You can see earlier when we hit 2 pi, we never go down to 0. But now when we hit 2 pi, we really go down to 0. So this say suddenly our qubit quality factor in the control become very high. Okay. Right. And this was earlier, what we did earlier when we control the excited state. You can see many oscillations, but you know what? It doesn't matter. The quality factor is only about 50% because this thing never go down to 0. And the other one, we have about 95%. Now let's look at what happens when you drive this two-level system using a continuous wave. Right. Earlier, we just used a single pulse. Then I'll come out here and put a pi pulse. Then I will see the highest emission. I put 2 pi pulse. I will see the thing go down to minimum. Now what happens if I have this thing continually drive, okay? Continuously drive, then, of course, when you look at quantum dot, suppose it only sees some kind of intensity coming out, right? Because if you look at time average. But really, during this time when it's coming out, this quantum dot evolution is really going up and down, up and down, up and down. Okay, so really, if you use the very, very low, say if before it complete the Rabi cycle, if the photon, if this exciton already emit the photon, then it's look at its emission spectra, you will see one single peak. And the width of that is just the lifetime of the this quantum dot. But what happens if you, before it decay, this thing go up and down many times, then what will happen is you will see triplet. And this is the famous called Marlow triplet. And then, okay, so you have a quantum mechanical explanation. That is, if this thing is driving up and down, quantum mechanically, this single line will split into what we call Dretz state. And Dretz state, the splitting is your Rabi energy, okay? And so the stronger the field, the larger this splitting is. Now, if you then look at, now if they create such a state, then these are all allowed transition, okay? These are all allowed transition. Some transition will retain the old transition energy, some transition will show shorter, will show smaller energy, and some will show higher energy, and it will become like that. And in fact, the intensity here will equal to the intensity of these two sidebands together, or equal to the sum of the two sidebands. And there is a simple explanation, okay? Let me just say, well, you know, sometimes if I have to give this lecture to people doing electrical engineering, so sometimes if you throw this thing called sideband, Dretz state, it drives them nuts, okay? So there is a very simple explanation. Say, oh, okay, if I think about this emitter, an emitter usually will just emit electromagnetic wave radiation, and this is the time, right? This is the wave. Now, if the probability that it's emit is being modulated with Rabi frequency, then it's like this is a single wavelength, and you just put this envelope modulation, right, in time, right? So, of course, this is much finer than that, and but I will not be able to write it, so I just put this one. So almost like the Rabi time is only 10 times an optical cycle, but in fact, the Rabi time is probably 1,000 times of the Rabi cycle, or even 10,000 times of Rabi cycle. But if that's the case, then what you're going to see, their emission is going to coming out, go like this. So if you make a Fourier transform of a function like that, what do you get? You get exactly one main band and two sideband. And the faster you modulate this, the more this sideband get pushed out. The slower you modulate them, the narrower this sideband. So the faster you modulate means you have a larger Rabi energy, and that is a explanation. Okay? Now, how do we observe this? So what we did was, if you remember, this is like almost like the time when the electromagnetic wave will come out, right? Then if I take such an emission, I let it interfere with each other, then I will see the interference, then it will look just like that. Okay? And that is exactly what we did. So what we did was we take the emitter coming out, then we split them, then we have the other stage, then it becomes cell interference to itself. Then we will see the interference, okay, and that fringes contrast is what we usually call the first order correlation function. And the first order correlation function, so what we did is now we can see now this also this interference amplitude, so this envelope, now indeed go through this modulation. Then if I can fit this with an analytical function and then make a Fourier transform back, then indeed it will correspond to the model triplet. But when we send this paper out to referee, to PIL, the referee was very mad, said you cannot call this model triplet because you look at things in time domain. Okay, so, all right, so we just correct it. We just say, well, it's a first order correlation function. It would correspond to the model triplet in spectral domain. So, and indeed, the Rabi energy that we deduce from that scale with the square root of intensity, just like what one expected. Now, then we decided, okay, since we got criticized of looking at things in time domain, why don't we look at things in spectral domain, okay? So this is how we did it. So you know the spectrometer only have a resolution about 100 to 200 micro EV. And the triplet we are really looking at, this is only a few micro EV, 10, 20 micro EV apart. And there's no way you can see them in spectrometer. So how do we achieve that? What we did is we send the light go through a Fabry-Perot resonator. So this Fabry-Perot resonator is high finesse. So it has a line width about 1 micro EV. Okay? And then you can just scan the distance between this Fabry-Perot resonator. Then you will be able to scan the loud transmission. Okay, light. Then of course, then before it hit the next Fabry-Perot resonator mode, then this what we call free spectral range has to be larger than the spectrometer resolution. So in this case, we have the free spectral space about 300 micro EV. So if it is go to beyond that, then the spectrometer can tell where it is. So in that, then we start scanning this distance between the Fabry-Perot resonator. Then we just pass through the light only very, very fine energy resolution. So by doing so, we have about 1 micro EV energy resolution. Of course, I will tell you, in this geometry, you lose a lot of light go through this Fabry-Perot resonator. On the same setup, we can also send this out, then we can let it go through the Hembree, Brown, and Twist correlation measurement, then that will tell us the second order correlation function. I will go to that later. But now indeed, okay, now you see this thing. You see the model triplet. Beautiful, okay? And not only that, indeed, the main band is exactly the sum of the two sideband. Let me see if I seen, okay, I didn't have this paper published in Nature Physics, and then at the same issue of Nature Physics, you've seen another group also seeing model triplet, but they have to look at it in logarithmic scale. Okay, they have to plot this in log scale, and their main band shot up about 2 or 3 orders of magnitude than the sideband. You know what that means? Means their laser scatter background still about 100 times than the emission. And in this case, it tells us the laser scatter background is 0. Okay, so now